In this video, we're going to be talking about models for logistic growth. In this section, we will use differential equations to model population growth. We will mostly focus on the law of natural growth and the logistic equation. The law of natural growth says, suppose you have a population of bacteria, for instance, with size p equals 500, and a certain time the population is growing at a rate of p prime equals 300 bacteria per hour. Now, let's take another 500 bacteria of the same type and put them together with the first population. Each half of the combined population was previously growing at a rate of 300 bacteria per hour. We would expect that the total population of 1,000 bacteria to increase at a rate of 600 bacteria per hour initially, provided there's enough room and nutrition. So if we double the size, we double the growth rate. It seems reasonable that the growth rate should be proportional to the size. In general, if p of t is the value of a quantity at time t, and if the rate of change of p with respect to t is proportional to its size p of t at any time, then we have the differential equation dp dt equals k times p, where k is some constant. If k is positive, then the population is growing, and if k is negative, then the population is decreasing. Let's solve for the solution of this differential equation that is sometimes called the law of natural growth. So we have dp dt equals k times p, and we're going to solve this using separable differential equations. So I'm going to move the p to the left-hand side. So I have 1 over p dp, and then on the right-hand side I have equals k times dt. I'm going to integrate both sides, and from here we get that the natural log of the absolute value of p is equal to k times t plus some constant. To get rid of the natural log, I will have the base be e on both sides. So if I do that, I get the absolute value of p equals e to the power of kt plus c1. And so the absolute value of p equals, I'm going to use an exponent property to split up my right-hand side of my equation. So this is the same thing as e to the c1 times e to the kt. And now what I want to do is I want to drop the absolute value sign on p, and to do that, I get p equals plus or minus e to the c1 times e to the kt. Now, plus or minus e to the power of c1, that is just some constant. So what I'm going to do is I'm going to replace that with a more general constant, capital C. And finally, we get p equals c times e to the power of kt. So formally, here's the solution of the initial value problem, dp dt equals kp, where p of 0 is equal to p naught, and the solution is p of t is equal to p naught times e to the power of kt. Let's talk about the logistic model. A population often increases exponentially in its early stages, but levels off eventually and approaches its carrying capacity because of limited resources. So the logistic differential equation is given by dp dt equals k times p times the quantity 1 minus the fraction p over m, where p is the population after time t, k is some constant, and m is called the carrying capacity of the population. Let's go ahead and solve for the solution. So we have dp dt equals k times p times 1 minus p over m. I want to divide both sides of this equation by p times 1 minus p over m. And then on the right-hand side, we're separating our differential equation, so we have k times dt. Now, on the left-hand side of my equation, I want to multiply the numerator and the denominator by m. And that's okay because I'm just multiplying by a form of 1. So if I multiply by m over m, that's going to give me m over p times, and I'm going to go ahead in the denominator, I'm going to distribute the m to both of these terms. And if I do that, I get m minus p and now we can go ahead and integrate both sides. On the left-hand side, we're integrating with respect to p, so capital M is serving as a constant. So if you recognize from a previous section, we need to integrate the left-hand side using partial fraction decomposition. So let's come off to the side here, and I have m over p times m minus p, and I want to rewrite this as a constant over p plus some other constant over m minus p. I'm going to multiply through by the least common denominator, and clearing that fraction will give us capital M is equal to a times m minus p plus b times p. And what we can do now is we can choose some special x values. So I'm going to say let x, or not x, our variable here is p. So we can let p equal 0. If we do that, we get capital M is equal to a times m minus 0 plus b times 0. And then that's equal to 0. So we get m equals a times m, and that implies that capital A is equal to m divided by m is 1. All right, so now we have capital M is equal to 1 times m minus p plus bp. And another choice of p we could do is we could say let capital P equal capital M. If we do that, we get capital M equals m minus m plus b times m. And if we solve for b here, by dividing both sides by m, we end up getting b is equal to 1. So I'm going to go ahead and clean up my screen a little bit. Okay, so through our calculations, we found that a and b were both 1. So coming back to our integral, we can get the left-hand side of our equation from previously will change into 1 over p plus 1 over m minus p dp is equal to the integral of k dt. Now, if we integrate both sides, the left-hand side, I will get the natural log of the absolute value of p. And remember, our variable here is p, so if I were to use u substitution there, because there's a negative, I'm going to have minus the natural log of the absolute value of m minus p. And then the right-hand side is going to equal kt plus some constant, c1. What I want to do next is I'm going to go ahead and, to my entire equation, I'm going to multiply my entire equation by -1. And if I do that, we get the natural log of capital M minus P minus the natural log of the absolute value of P is equal to negative KT minus C1. I'm going to cross out the page number here, so ignore that. Now on the left-hand side, I can combine the two logarithms into one logarithm using the quotient rule for logarithms. So I get the natural log of M minus P over P is equal to negative KT minus C1. And if I apply E on both sides, I can get rid of the natural log. I'm going to split this up using the exponent rule, so I have e to the negative c1 times e to the negative kt. And I'm going to move up here. So dropping the absolute value bars, we get m minus p over p is equal to plus or minus e to the negative c1 times e to the negative kt. Now, on the left-hand side, what I can do is I can split that up into two fractions. So I have m over p minus p over p, which is 1, equals, and plus or minus e to the negative c1 power, that is just some constant, and I'm going to call that constant capital A. E to the negative kt. I'm trying to solve for p, so I'm going to go ahead and add 1 to both sides. And I'm trying to solve for p, so if I do some algebraic manipulation, we're going to end up getting that p equals capital M over 1 plus capital A times e to the power of negative kt. So we did all of that work to show the solution to the logistic differential equation dp dt is equal to k times p times the quantity 1 minus the fraction p over m, where p of 0 is equal to p naught, and the solution is the thing in the box we see, p of t equals capital M over 1 plus capital A times e to the negative kt, where capital A is m minus p naught divided by p naught. And remember, m here represents our carrying capacity, and p naught represents our initial population.